Okay, well, yeah, I'm really very happy to introduce Professor Pavel Pudlák to you of the Mathematical Institute of the Czech Academy of Sciences. So yeah, so Pavel's early work was about things like consistency statements, cuts, and interpretability, and later he moved towards more towards things like proof complexity and complexity theory. So yeah, so if you so Pavel always was one of my favorite colleagues, because his work was always extremely inspiring. And I think that if you look at the list of his publications, that still doesn't do justice to him, because he's also very good at asking the right questions and pointing the way in interesting research directions. So today he is going to speak to us, and now I have to look. So on a journey from Peano Arithmetic to proof complexity, and so I'm happy to give the floor to Pavel.
Thank you. I will share the slides first, and then, let me start by thanking to the organizer, to Professor Yong, to invite me to give this lecture. Let me say that if you don't hear me very well, just tell me, or if something is wrong with the sharing of slides, also this can be fixed. And certainly you can ask questions anytime you want. I want to apologize for giving a rather survey elementary talk, because I didn't know what the audience of this lecture will be. So I decided not to be technical. And also I decided to do a bit historical survey. And the reason is that if I just started explaining the concepts and results without putting them into the context, how we arrived to these questions and problems, then it may be it may look not so interesting, but everything has its history, and history explains why particular concepts are studied. But I should also make a disclaimer that I'm not a historian, so my historical notes should be taken with a big grain of salt. So let me go to the slides. So here is an overview. I will not read it, just you can have a look at it a little bit. But let's go on. So the topic is Peano arithmetic and propositional logic, propositional calculus. Why do we care for propositional calculus? Let me be a bit personal. When I started studying logic, I took some books and read about logic, for instance, the famous Schoenfield's mathematical logic and other books. And I always skipped propositional logic, because for me, propositional logic was decidable. So why should we care how it is formalized? And as it happens so often, that what you think that is unimportant and uninteresting, you later find out that this is really an interesting and important topic. And so this happened also with me and the propositional calculus. So let's start from the beginning, not from Greeks, but just origins of arithmetic. Of course, arithmetic was known to Greeks, but I would like to explain Peano Arithmetic. So when did Peano Arithmetic appear? Axioms of Peano Arithmetic are attributed to Richard Dedekind and Giuseppe Peano. They formalized arithmetic in what we now call a second-order logic. The reason is that they use the concept of set. They were right in this sense that arithmetic is completely determined by the principle of induction, but it depends also how we formulate it. As a first-order logic, I think it appeared in the school of David Hilbert, probably already before 1920s. The reason being that before there was no concept of first-order logic. So logic was just formalization of logic was just developing in the works of Frege and Bertrand Russell. But by 1920s, they already were aware that, that there is something like first-order logic, and they defined what we now call Peano Arithmetic in this logic. If you want to formalize arithmetic in first-order logic, then it does not suffice to use the successor function, because such a theory, successor function, and the induction for formulas with successor function is trivial. It's just very simple theory about the successor function, but it becomes non-trivial if you use the basic arithmetical operations as primitive concepts, that is plus and times. So first, what one needs is to state some axioms that determine these primitive concepts, the successor function, addition, and multiplication. And then we add the scheme of induction for all formulas in the language with these symbols. So the first mistake that I see here, I had also axioms for less than or equal to, and then I forgot, then I deleted them and left the symbol here. The thing is that we may include this into primitive symbols, or we may define it. So the induction is stated for all formulas in the language of what we call language of arithmetic, which is the successor, plus, and times, and zero. In the Hilbert school, it was not called Peano Arithmetic. It was denoted by Z. The modern notation is Peano Arithmetic and the abbreviation PA. The question that the Hilbert school or Hilbert was interested in were two main questions about Peano Arithmetic. Is Peano Arithmetic complete? And is Peano Arithmetic consistent? This, let me go back to formalization. The formalization was possible by developing proof theory. This was the idea of Hilbert was that one should develop proof theory, the theory of proofs, how mathematicians prove theorems, and then he want to use this theory to solve these problems, namely to show that say Peano Arithmetic is complete and Peano Arithmetic is consistent. And the main thing that he was interested was the consistency, because he was very disappointed by the directions that by the new direction that appeared in the foundations of mathematics or philosophy of mathematics, which was intuitionism. And he wanted to give an alternative to this approach by proving that by axiomatizing the basic systems, basic structures in mathematics, and proving that these systems are consistent. And once these systems are consistent, that there shouldn't be any objections to use these systems. But one should know that he was not interested just into Peano arithmetic. He also considered this arithmetic formalized in second-order logic, and that was before it was understood that second-order logic cannot be formalized effectively. This program was shattered by the work of Kurt Gödel. He proved he essentially answered both questions negatively. He proved that Peano arithmetic is incomplete, and he also proved that the consistency of Peano arithmetic is not provable in itself, which means that it's not provable in any weaker system that we may consider as finitistic. The idea of Hilbert was to prove the consistency in some systems that were finite or finitistic, and this shows that this is not possible, and if you have stronger theories, then the same theorem applies, and the problem is even harder to prove the consistency. In these proofs, there were two main ideas. One was that it's possible to encode finite structures in Peano arithmetic. He needed this to formalize syntax in Peano arithmetic in order to talk about provability in Peano arithmetic, namely, or we can say that he showed that it's possible to formalize syntax in Peano arithmetic. And the second important idea was that it's possible to express self-referential statements. Self-referential statements were not new. They actually appeared when the paradoxes appeared. But let me talk about the first thing. The first thing means that Peano arithmetic is not just a theory about integers. It's a theory about all finite structures, not only numbers. It's a theory that is equivalent to finite set theory. This is stated here as Peano arithmetic equivalent to Zermelo-Fraenkel set theory, where we replace the axiom of infinity by the axiom of finiteness, saying that all sets are finite. But why is Peano arithmetic incomplete? We know from the work of Godel that it's incomplete because it doesn't prove its own consistency. But does there exist a stronger principle than induction, or what is missing that it is incomplete? The point is that it's not that the principle of induction does not suffice to characterize natural numbers, but Peano arithmetic intuitively is incomplete because the induction scheme is stated only for arithmetical predicates. And later research showed that it depends, or already at this point it may have been clear that it depends for which predicates you state the principle of induction, and according to this you get stronger or weaker theory. This in particular can be shown on the arithmetical hierarchy of formulas. Let me recall what bounded quantifiers are. Bounded quantifiers are quantifiers where the range of quantification is bounded by some value which is expressed by a term. So here T stands for a term. And this notation is just an abbreviation of these formulas. Starting with this, bounded formulas, which are formulas where all quantifiers are bounded, we can define the hierarchy. So sigma formulas are formulas where all quantifiers are bounded. The notation for this is such that we can use either sigma or pi or delta 0 for this set of formulas. And then we can go on. Sigma n formulas are formulas where unbounded quantifiers alternate, and after that we have a bounded formula. Similarly for pi and formulas. Given sets of formulas, we can now define, we can classify sets of natural numbers. Sigma n sets are those that are definable by sigma n. Pi n sets are the sets definable by pi n formulas. What is important is that the hierarchy of these sets is strictly increasing. So if we use sigma n and pi n for classes of sets rather than classes of formulas, we can write it as these inclusion and non-equalities. Of course, you know that there are other relations between these classes, but what's important is that as we take more complex formulas, we are able to define more sets. And this is reflected also in fragments of Peano arithmetic. By fragments, I mean sub-theories of Peano arithmetic. Given the class of sigma n formulas, we can restrict the induction scheme to formulas that are sigma n. This is usually denoted by I sigma n, induction for sigma n formulas. And as similarly as the hierarchy of definable sets, also this hierarchy is strictly increasing, which means that I sigma n plus 1 proves more sentences than I sigma n. So this shows that if we have the possibility to express more predicates, or if we apply to induction to larger class of predicates, then we can prove more sentences. Among these fragments, there are two that are important. The first one is I sigma 1. And this is induction for sigma 1 formulas. This is a theory that is related to another theory called primitive recursive arithmetic. And primitive recursive arithmetic has a richer language. It has symbols for all primitive recursive functions. So it's defined in a different way. But if we restrict to the common language of these two theories, then I sigma 1 is conservative. That is, it proves the same theorems that arithmetical theorem as primitive recursive arithmetic. So here we see that the first connection between theory and computability, because I sigma 1 is connected very much with primitive recursive functions. I don't have a slide for this, but we will have a similar theorem for in bounded arithmetic. The smaller of the two fragments is I sigma 0, which is induction for bounded formulas. Now let's now look at what happens in computability theory. In the 1960s, people started to investigate more restricted types of computations, because they realized that the concept of computable function doesn't capture very well what is computable in practice. A computable function may require very long time to be computed, or very big memory. So they started investigating computation with restricted resources, and the resources, the natural resources to consider were time and space. In 1971, a very important and seminal paper appeared, which in which Stephen Cook introduced the classes P and P. I suppose that you know what these classes are. If not, then just imagine P as the class of efficiently computable sets, and NP is the class of efficiently verifiable sets. Verifiable in the sense that one can, if you have a solution, you can provide a proof that the solution exists, or you can view it as adding a quantifier to this. A little bit later, Stockmeyer realized that we can define a similar hierarchy as the arithmetical hierarchy, which extends the classes P and NP in the natural way, where the smallest class, sigma P0, is P. The next one, sigma P1, is NP. Pi P1 is co-NP, which means these are complements of sets in NP. There was another very important seminal paper in early 1970s. This was a paper by Rohit Parikh, Existence and Feasibility in Arithmetic. This paper contained a lot of interesting ideas, and one of them was the system that he called PB, which is equivalent to I sigma 0. The reason why he defined the system was that he realized that sigma zero sets are fairly efficiently computable. They are computable in linear space. Now, we know linear space is not as efficient as P, because for all what we know, something in linear space may require exponential time to be computed, but still it was much more restricted, much more feasible it was much more feasible to decide sigma zero predicate than say sigma one. He was presenting a kind of a finitistic approach to the foundations, and he called PB an anthropomorphic system. And I should say that there are other interesting ideas. In particular, what is very interesting in this paper is the idea of almost consistent theories. But describing this would take us probably too far afield. So by the influence of the complexity theory resulted in bigger interest in these weak systems. Two people who started systematically studying these systems were Paris and Wilkie. Their main paper appeared only in 1981, but they worked on these and had some preprints and partial results already in mid-1970s. They considered essentially the same system, I sigma zero, but they used delta zero instead of sigma zero. But we know that this is the same. A little bit later, Samuel Bass came up with the concept of what he called bounded arithmetic. These were theories that postulate induction for formulas in the formulas that define sets in the polynomial hierarchy. What he wanted essentially to do, he wanted to define a hierarchy of systems such as I sigma n, where these would be subsystems of I sigma zero or slightly stronger system. These theory S2 and T2 were stratified also in fragments, and these fragments corresponded to set sigma Pn of the polynomial hierarchy of Stockmayer. Let me now explain something slightly technical. What Paris and Wilkie did, and Samuel Bass as well, was that they considered slightly stronger theories than I delta zero. And the reason was that in I delta zero, we cannot formalize polynomial time computations. The reason is that if we want to formalize computations, then we may use binary representations of numbers to encode strings. But then if we have a string of length n, we need to be able to produce or to talk about strings of length polynomial in n, say n to c, where c is some constant. If you consider what it means for the size of numbers, this means that from n that represents strings of a string of length n, we need to produce a number m that represents a string of length n to the c. So this means that log m should be approximately log n to the c. And that means that m should be approximately 2 to the log n to the c. And this can be written as n to the log n to the c minus 1. So if c is larger than 1, then this is clearly larger than n to a constant, which means that it's larger than what we can do in I delta 0, because in I delta 0 we can only prove that if there is a number n, then there is at most polynomial larger n. So therefore, they strengthen the theories by additional axioms. Paris and Wilkie just added an axiom called omega 1, that for every x there exists a y which is of the size x to the log x. Now, they did not extend the language with exponentiation, because then the theory would be too strong. So this expression of y equals x to the log x is just an abbreviation for a formula that expresses this relation. And this relation can be expressed in arithmetic in a suitable way, although it requires some technical work. And Bas instead added a function symbol for something similar, which is the symbol which represents the binary function, binary operation or function that produces from x and y a number that from the point of arithmetic is not very interesting, is 2 to the something. But the important is that the length of this number, of the length or the length of the string that this number encodes, is the product of the lengths of x and y. So this is one technical thing that one has to take into account when you formalize computations in weak theories. So therefore, what they studied was not exactly I sigma 0, but something slightly stronger. So let's look at Bas's fragments. I will only mention one, and I will not define it explicitly. Let's just say that this is the fragment in which one is able to formalize polynomial time computations. And the perhaps most important result in his theory was that he showed that if we have a formula that formalizes polynomial time computable relation, so we can formalize polynomial time computable relation very naturally in the system. I will explain it later in terms of sharply bounded quantifiers, but for now, let's just take it as some formalization of polynomial time computable relations. And if this theory proves that for every x there exists y, such that x and y satisfy a formula phi, then there exists a polynomial time computable function f such that for every x, x and fx satisfy this relation. So this gives a very tight connection with computations, and therefore we associate S12 with the class P. We think of this theory as a theory that in the realm of theories corresponds to the class P in the realm of computational classes. So another thing that influenced people who started working on these problems, or at least it influenced me, because I finished, I was finishing my studies in the mid 1970s, was the discovery of mathematical sentences unprovable in Peano arithmetic. The problem with Godel theorem was that it did give a sentence unprovable in arithmetic, but it was a kind of ad hoc sentence. It was a sentence about logic, also a very interesting sentence because it talks about consistency, but it was not a mathematical sentence. Paris and Harrington discovered a version of the finite-Ramsey theorem, a very well-known theorem that is unprovable in Peano arithmetic. They just modified the statement of finite-Ramsey theorem and showed that this modification is not provable in Peano arithmetic. So this was very exciting, and people were hoping that we will be able to prove some independence for problems that were open in number theory and finite combinatorics or complexity theory. But unfortunately, this sentence is a pi2 formula, and the most interesting sentences are pi1. So, for instance, the Fermat's last theorem is pi1, or the Riemann hypothesis is pi1. P unequal NP is not pi1, but in a sense is very close to pi1. We don't expect that it would be something like the Paris-Harrington sentence. And the method by which Paris and Harrington proved their independence didn't work for pi1 sentences. And we wanted to prove independence for these interesting sentences. People were hoping that this may happen, but it turned out that it was not so easy. And in fact, Fermat's last theorem is provable already in I sigma 1 in the relatively weak fragment of Peano arithmetic. So we need a new method if we want to prove independence of pi1 sentences. And since we don't know what to do, we should try to prove independence from weak fragments, because if the theory is weak, then more likely one can prove independence. So these two things, the relation to computational complexity and the ability to prove independence for stronger theories, led people to focus on weak fragments, such as I delta I sigma 0 plus the axiom omega 1 and Basse's theories. But let's now go to propositional calculus, which is the other topic of this talk. I will explain a connection between theories and provability in theories and provability in propositional logic. Let's define the class of formulas called sharply bounded, and these I'm not sure I have I don't have an exact definition here on the slide, so let me just say it in words. A sharply bounded formula, the main thing is that it's decidable in polynomial time. And the way it is defined is that we consider quantifiers that quantify, that restrict, bounded quantifiers that restrict the range of quantification into logarithmic. They bound the range by logarithm. And in this way, the formula can be evaluated by considering all possible values, and this gives a polynomial algorithm to decide these formulas. Every pi1 formula is equivalent to the universally quantified sharply bounded formula. And now, if we have a sharply bounded formula, we can construct a sequence of propositional formulas which express the same thing as the formula phi, but the propositional formulas only talk about finite range. So we have the equivalence that the formula phi is satisfied by x1 and xk, each less than n, less than or equal to n, if and only if phi in brackets n is a tautology. So this statement is just finite statement. It talks about numbers less than n, and these numbers can be represented in binary. And it says that this formula is satisfied for all these numbers. So if we introduce propositional variables for representing these formulas, then it is clear that we should be able to write down such a formula that expresses this first order formula, and that this formula is only polynomially large, at most polynomially larger than n. So if now if the formula universally quantified is true, that this is true with no bounds, then this holds if and only if this sequence of formulas is the sequence of tautologies. So the conclusion is that we can express pi1 formulas or we can express pi1 formulas by sequences of propositional formulas in such a way that the pi1 formula is true if and only if this sequence of propositions consists of tautologies. So this is not a deep statement. This is just a technical statement. You have to do a lot of technical details, but conceptually, this is clear that you can split the statement, a universal statement, into its finite parts, and the finite parts can be expressed by propositions because they are finite. But we'll see that it has some application, and these applications are that if the universal formula, the pi1 formula is provable in a weak theory, then tautologies have polynomial length proofs. So this is stated a bit not quite formally, because it depends how we formalize propositional proofs and how this theory is strong. But this is what was discovered, and this idea first appeared in another seminal paper of Cook, where he introduced not a first order theory, but it was an equational theory, which is not important, that it was just an equational theory. And he connected this theory with a particular proof system for propositional calculus. It was extended resolution, but I will not state the theorem in the way Cook stated it. I will state a theorem that appeared in Bass's book and his thesis, which was stated instead of this equational theory that again S12 is conservative over this equational theory, and it's stated for not extended resolution but extended Frege proof system. So this is a very important theorem that I want to tell you, because this gives connections between provability in first order theories and provability in propositional calculi. So the theory here is S12, and the theorem says that if the theory proves such a pi1 sentence, then the translations into propositional calculus, the sequence of propositions, have polynomial length proofs in a system that is called extended Frege proof system. The extended Frege proof system is not something ad hoc. It's a very natural system. It's a slight extension of the most usual systems that people use to formalize propositional proofs. It's an extension of so-called Frege systems, where Frege systems are systems which are based on rules and axiom schemes. So, for instance, a set of axiom schemes and modus ponens. The extension means that there is a rule that enables one to abbreviate a long formula by a propositional variable, because in general it may happen that as the proofs proceed, then larger and larger formulas are needed, while the proof itself doesn't have to be very long, maybe polynomial length, but it may have exponentially large formulas. Therefore, this extension rule enables one to introduce abbreviations, and such a proof then becomes of polynomial length. So this is the relation. And this relation now gives us the possibility to prove unprovability in S12 of a pi1 sentence by proving super polynomial lower bound on extended Fragment proofs. So suppose we would be able to prove some super polynomial, ideally, of course, exponential lower bounds on propositional proofs. Then we would be able to prove independence for S12. But unfortunately, we are not able to prove lower bounds on extended Fragment proofs. We are not able to prove non-trivial lower bounds even for Fragment proofs where we don't use the extension rule. Let me say a little bit more about this theorem. So the theorem is here repeated. This result is tied in the sense that the extended Frege proof system is the best possible. You cannot use a weaker system in this theorem. And this and similar connections were found between other theories. So we have theories and proof. We have, for some theories, we have associated proof systems that are of this form, that if the theory proves a pi1 sentence, that the corresponding proof system is able to prove by polynomial length proofs these tautologies, and one can also show that this system is uniquely determined by the theorem. Now, so I said that we are not able to use this to prove independence for S12, which is maybe sad because this is a weak theory and we were hoping to prove independence for much stronger. But one can still prove some independence. In this direction, the first result was also a milestone in this area of proof complexity and big fragments of arithmetic. Miklos Aitai proved the following theorem. So this is a bit more complicated slide, so let me explain it slowly. Consider a countable non-standard model of true arithmetic. So this model M can be a model of Peano Arithmetic, but we have but it can also be a model of much stronger theory. And in particular, for this theorem, let's take M to be elementary equivalent to the standard model of natural numbers. So in M, all sentences that are true in the standard model are true in M. And you know what a non-standard model is. It's a model where on top of the standard numbers, you also have non-standard numbers that are infinitely larger than the standard. The theorem says that if you take A and sufficiently large B, so there is a quantifier missing here. You can take any non-standard. Oh no, it's correct. A is you can take any non-standard number, and then you take sufficiently large B less than A. Then there exists a function from the interval 0 up to B1 on the interval 0 up to B. And here is an omission. I wanted to say that this function is 1-to-1, otherwise the whole thing would be trivial. So sorry for that. So this function is 1-to-1. And the function has the property that if you extend the model, but now you only take M restricted to this initial interval A, which means that you have to consider addition and multiplication as ternary relation rather than functions. So you have these basic operations, addition and multiplication, and then you add this function. Then you can define such a function that this model satisfies induction axioms for all formulas in the language of arithmetic extended with this function for f. So even if the formula refers to f, then you still can use the induction. So this is maybe surprising because we know that using induction we can prove easily the Prepositional principle, but here it is restricted to an initial interval of the model. So let me just repeat that this f should be 1-to-1, which means that this is an example where the Prepositional principle fails, while the induction is still satisfied. This is a model theoretical result, but it's equivalent to proof theoretical results. And in particular, what I derive from this is the statement that is actually equivalent to this theory in a sense, that there are no polynomial length proofs of the propositional tautologies expressing the Prepositional principle in depth D Frege system for any constant D. Now, what are the depth D Frege systems? These are just the usual systems that I mentioned before, where you have axioms and deduction rules. But you restrict the formulas that may be used in a proof. Let's consider the basis of connectives, just not, or, and. and say that the formula has depth at most d if there are at most d alternations of different connectives. So we may have large conjunctions and large disjunctions that there is no restrictions on that. But if you consider this tree, then they should not alternate more than d times. For example, if you take CNF and DNF formulas, say in CNF you have a conjunction and then disjunctions, and then you may have negations. So this this corresponds to depth 3, that you have 3 alternation. So this model theoretical result is equivalent to the result about the length of proofs in propositional calculus, except that we need to restrict we need to consider a more restricted system. But this also has consequences for the systems that we considered, namely I sigma 0, except that we cannot take just I sigma 0 itself, but we have to extend it in a similar way as we extended the model of arithmetic, namely we add a new function, since this is a syntactical thing, we add a function symbol, and we add induction for all bounded formulas in the extended language. So we take formulas that contain not only plus and times, but also f, and postulate induction for bounded formulas. But we do not add any special axioms for f. So f can be viewed as a second order variable or as a new symbol. This is equivalent. So then we can state the corollary of Aitai's result, that the sentence there exists a mapping from the interval 0 up to x1 to 0 to x, which is a one-to-one mapping. So here I did not forget about writing that it is one-to-one, which is the sentence is consistent with the theory I just described. So put differently, it means that this theory does not prove the pigeonhole principle for f. So here we have indeed an example where one can prove independence by proving a lower bound. And indeed, we don't have to use Aitai theorem. We just need to prove a lower bound on this form in order to prove the corollary. In fact, later on, people just proved lower bounds rather than using model theoretical results. And in this way, they were able to extend this theorem not just to I sigma 0 f, but to I sigma 0 f plus the axiom of omega, or equivalently to basis theories S2 and and T2. So, by the way, you might have been wondering what was the relation between B and A. The relation between BA and A corresponds to the lower bound that one is able to prove on propositional proofs. If you only prove a lower bound super polynomial, then this relation will be only that B cannot be more than slightly less than A. But if you prove exponential lower bound on these propositional proofs, then you can prove this theory where B is almost exponentially smaller than A. And this is equivalent, I mean, the relation between B and A is equivalent to how large a lower bound you prove for proof in this theorem. Okay, so is this interesting? Now, isn't it a bit funny that we were able to, we wanted to prove results about big mathematical problems, and now we are only able to prove unprovability of a trivial principle, PHP. So I've been talking for quite a while, so let's have a break in the sense that I will digress a little bit about to an episode about the PHP. I was in 2000. I was in Princeton, and there is a cafe that is used by people from the university and from the institute called the Small World Cafe, where people often go to discuss mathematics. And I was there with Ran Raz, who was explaining me his new proof about the pigeonhole principle. So we were sitting and he was saying, so these pigeons go here and those pigeons go there, and there are so many pigeons here and so many holes there and so on. So I thought to myself, so what people would think about us, that we are just counting pigeons in holes. Is this real mathematics? Or maybe they thought that actually we are doing something useful, not just counting numbers, but counting real things like pigeons. Anyway, so I digress. Let me get back to the question. So is the pigeonhole principle trivial? Of course, it is. It depends how you look at it. But if you look at it from the right point of view, it's not so trivial. From the computational point of view, you may consider this question. Given a Boolean circuit C with n inputs and n outputs, where m is smaller than n, then there must be a collision that two different inputs such that the outputs produce the same string. But how to find this collision? And this is considered to be in general hard. And this is used in hash functions and digital signatures and so on. So we don't think that this is easy. So from the point of view of computational complexity, this is certainly not a trivial principle. but also from the point of view of proof complexity. So consider the situation that is slightly different. Sometimes people call this the dual Peano principle, where the number of inputs is smaller than number of outputs, and take some string of length m, which is not in the range of the outputs of C, which is not in the image of C. And then the question is how to prove that B is not in the image of C. And this is, we don't know, but our experience so far is that this is difficult. And it may be, in fact, a generic problem that is difficult for any proof systems. Let's consider a special case of this last principle. So I copied this proof theoretical version of the Peano principle here, and consider the special case where we pick a particular circuit C. So we do it in the following way. Let M be let M have the form 2 to the k. So then we can view each string as a truth table of a Boolean function of k variables. So there are 2 to the k possible inputs for a Boolean function. Therefore, we can encode the Boolean function by a string of length 2 to the k. So this is what we will do now. Now let's view the strings of length n. Excuse me. As codes of small circuits of k variables. So n is n is smaller than n. So we certainly have a smaller number of circuits than Boolean functions. Now, the circuit C is just the evaluation circuit which maps the codes of circuits to functions, to Boolean functions. So it may be a bit confusing that now circuit maps circuits, but think of it just as an evaluation map that if you get an X, then you will produce the truth table of the circuit encoded by the string X. So this is the circuit C. Now let's look what it means that B is not in the image of C. It means that the Boolean function B doesn't have a small circuit, because if say we encode by this all small circuits, then this means that B doesn't have a small circuit. So this principle actually is connected with proving lower bounds. So here I said that it may be difficult to prove that B is not in the image. But now we have a concrete thing. We want to prove a lower bound, and it seems that proving lower bounds is difficult. And this is what we want to understand. Why are we not able to prove lower bounds on Boolean circuits. So the bottom line is that things that may look easy and trivial actually are not so trivial and may be connected with the deep problems. So let me now say what the general concept of a proof system is. Here I mean proof systems for classical propositional logic. This was another paper that was seminal in this area, in which the general proof system was defined. It's a very natural concept. I think everybody would eventually come up with the same thing. The proof system is any binary relation that should express the relation that y is a proof of x, such that it is sound, it is complete, and it is decidable in polynomial time. So the soundness and completeness are things very natural that we would expect, but also the decidability, because what a proof should be is something that we can read and see that it actually is a proof. So we should be able to check that it is a proof, and this is expressed by the third condition. So once we have this general concept, we are not bound to consider the proof systems introduced before and their variations, and we can look for any possible proof system, which I will do in a moment. But I still need to introduce another concept, and this is the question of the length of proofs in the proof system. So let's say that the proof system is polynomially bounded if for every tautology we can find at most a polynomial longer proof, if there exists at most polynomial longer proof. So this leads to the following fact that was observed very early in this area, that there exists a polynomially bounded proof system for propositional tautologies if and only if NP equals co-NP. So this statement NP equal co-NP, or rather its negation, is weaker than the negation of P non-equal NP. So it may happen that P is not equal to P, but NP is equal to co-NP. But most people believe that NP is not equal to co-NP, which means that we may consider other proof systems, but we should not expect that we find a polynomially bounded proof system. So, as I said, once we have this concept, we can consider various non-logically defined proof systems. And I would like to briefly mention just one system, which is from the area of integer linear programming, ILP. In integer linear programming, the basic problem is given a system of linear inequalities, find an integer solution or prove that there is no such solution. You certainly know linear programming, where we just ask about any solution, but it's also an important version, this integer solution, and this is NP-complete. So this is hard. Linear programming is solvable in polynomial time, but this is NP-complete. But the fact that it is NP-complete means also that we can reduce the satisfiability of Boolean formulas to integer linear programs. So we can use it as a proof system, but in fact the formalization or reduction of Boolean formulas to linear inequalities is very straightforward. Here it is shown on an example that if you want to express a clause x or y or non-z, then this is equivalent to the linear inequality of this form. So this means that that propositional logic is in a sense embedded into integer linear programming, and any method for solving ILP can be viewed as a proof system. This was observed for a particular method of solving integer linear programs that was proposed by Godel, and it is called cutting planes. Cook, Coulard, and Turan observed that, or they explicitly presented this method as a proof system for refuting unsatisfiable CNS, or equivalently for proving DNF tautologies. And this is one of a few situations where one can prove exponential long proofs on exponential large bounds on proofs in concrete systems. So that there is an exponential lower bound on cutting plane proofs. So this can be also viewed as a proof that if you take the cutting plane method, so this was not an algorithm, this was just a method that you may formalize in various ways to make different strategies how to cut the planes, so to say. But the theorem shows that whatever algorithm you base on the idea of cutting planes cannot be polynomial algorithm. So any algorithm that only uses this cutting plane method must run in exponential time. So we are not able to prove P unequal NP, but at least in some instances we are able to prove that the particular algorithms cannot solve NP-complete problems. So one thing I want you to take as a take-home message is that that proof complexity is not just the study of the length of proof. That proof complexity is connected with formal systems, with first-order systems, So we should view it as a study of all weak formal systems and systems connected with feasible computations. I have still one more example, and I'm afraid that you may be already tired, so I can stop here or present it, but...
Yes,
so,
I think
sorry?
I think you can finish your slide. Yeah. Just
I should finish. Okay.
No. I mean, you continue on and finish.
Oh, continue. Okay.
Yeah.
So if you want to hear a little bit more, so this is another way, another thing that I want to say about proof complexity, that it enables us not only to study the usual complexity of problems, but also proof theoretical complexity of computational problems. If you have a computational problem, this is not a formula, not a theorem that we could ask, is this provable or not? So it's a problem to solve some task. But what we can ask is, what is the weakest theory in which we can formalize and prove the soundness of an algorithm for this problem P? So some problems, so every algorithm for a non-trivial task, at least, must have some idea, must be based on some idea. And this idea is a mathematical idea. And this idea may be provable in weak theory, but it may be not, may be provable only in strong theories. So here's an example. So this was something that we observed a long time in Rome. And it's a conditional result. It's a result based on the assumption that factoring of integers, factoring of composed integers is hard. So under this assumption, S1, 2 cannot prove the soundness of any algorithm for primality. So if A is any algorithm for primality, then S doesn't prove its soundness. And it's stupid to give a proof at the very end of the lecture when people are tired, but this is a very simple proof. If suppose A is a polynomial time algorithm for primality, and suppose S12 proves that if this algorithm says no, the X is not prime, then there exists Y and Z less than X, such that Y and Z is equal 1. Should the theory prove the soundness of the algorithm AX, then it should prove this. In fact, the soundness is an equivalence that there are such numbers if and only if the algorithm says that it is not a prime. And then by Bassis' theorem, there exists a polynomial time algorithm. So this is formula for all. There exists Y. So there must be a polynomial time computable function, a polynomial time algorithm that given a non-prime, we can find a factor. So F would compute factors of non-primes. So therefore, such an algorithm does not exist. So this was a long time ago. It was before the AKS deterministic algorithm was known. But now we know that this particular algorithm, because it concerns all algorithms for primality, so also this particular algorithm is not provably sound is S1 too, unless factoring is easy. So if we believed in this assumption that factoring is hard, then we have an example of a lower bound on the proof complexity of an algorithm. This algorithm cannot be proved sound in S1 too. And this seems very much to be true. So my students tried to formalize it, and it turned out that much larger theory is needed to formalize this the soundness proof of this algorithm. So here are some books I can recommend for reading if you are interested, and thank you very much for your attention.
Thank you, Pavel, for this wonderful lecture. So, yeah, so are there questions?
Can I ask a question?
Yes.
So you mentioned the Fermat's last theorem can be proven in I sigma 1. Are there any references for this? The last time I heard is people do not even know whether it can be done in PA.
Okay, yeah, so maybe I a bit exaggerated, but I was in Oberwolfach when Angus McIntyre talked about it. So apparently he researched this very carefully. Also, when I asked him about any manuscript about it, he said that he doesn't have anything complete that he would present, but he strongly believed that this is possible. So there is no paper that shows this.
Okay.
Of course, the original proof was not even in the ZFC. It required some attendant universities, but all these things can be avoided.
Okay, thank you.
This is a question from Sansando. His question is that in light of the recent result on set solving, do you think we need a new version of combined thesis? This thesis is that intuitive notion of easy hard to compute is equal to it's just computable in the classes P or NP. It is the like Turing thesis.
Okay, so I still did not get exactly your question, but did you mention SAT solvers or what?
Yeah,
I think the question was about do we have to search for new notions different from p-time computability in the light of the lack of success of the present studies? Something like that, Yong?
Yeah.
Yes, yes. So this is what I thought you were asking. So you probably mean that the SAT solvers now are able to solve really huge instances of the problem of satisfiability, and the question is whether we should not rethink the classical approach where we consider NP-complete problems hard, because this is an NP-complete problem. But you know, these SAT solvers are also used for proving unsatisfiability or proving tautologies. And they fail for very simple tautologies like the pigeonhole principle. And so the research still confirms that that we are right. That just it's difficult to see it if you consider satisfiability of formulas, because these are rather complex things, and the industrial examples are things that I don't know, but we know very well from graph theory that there are incomplete problems like finding a large clique or finding a Hamiltonian circuit. And if you take a random graphs, then these problems become trivial, because you take a random graph, for instance, then it never has a large clique, so you have to take a random graph with the probability of an edge is fairly large, and then on the other hand you find a large clique easily. So this is for me this is not the reason to change our approach.
Okay, so
does it answer your question or answer something else?
Yeah, I have posted a question in the chat box. So you agree with this thesis?
Okay, I should read the chat.
Yeah, so I'm still unmuted. So the chat says, do you agree with the following thesis?
Yes, I see.
You have it? Yes.
Yes, basically I agree, yes.
Okay. Yeah. But for this, is it possible to give a proof? Just some philosophically justification for this thesis, just like a Turing thesis?
Well, you cannot give a proof to Turing thesis. It's just a thesis. And this is also a thesis.
Okay. Yeah. Another question. Just all the natural concrete incompleteness sentence, just the independent sentence from PA with natural mathematical meaning. Its complexity is higher than pi 1. For example, the sigma 2. Is any example of this natural incompleteness sentence whose complexity is just pi 1, just similar to Godel sentence?
So there are no pi 1 sentences that are proven to be independent of Peano arithmetic or other theories that are so mathematical as this Paris-Harrington version of the finite Ramsey theorem. But Harvey Friedman claims that he has concrete sentences independent not only from arithmetic, but independent from extensions, very strong extensions of set theory. Unfortunately, as far as I know, he hasn't published a proof of this, but he has these sentences stated on his web page. And these are very complicated sentences, which is hard to connect with anything that was studied in mathematics. So maybe Fyodor knows more about it.
Yes. So actually, yes. So now Harvey have new sentences that look simple than the ones that he had 10 years ago in his Boolean relation theory. So yeah. But they also are not published. So
they are also not published.
Yeah, yes. But they're nice.
So Fedor, are you going? He's giving now a lecture series about this, right? Are you attending that? Okay.
Yes, so he is giving this lecture series
So were the lecture series on Zoom or some?
Yes,
Yeah.
yes, on Zoom, yes. So you could contact Andres Weirman if you want to join.
Okay, okay. Yes, I didn't know about it. Yes, I'd be interested, sure. Yes, but
Oh,
it's not, I mean, it's not that surprising, because if you somehow play with the consistency and try to somehow rewrite it, then I believe that eventually you should come with something looking more mathematical. But of course, he has worked on it for a long time, so he has much better sentences.
okay, more questions. So I have a question about the pigeonhole independence from I delta 0 plus f. Can you demand more all kinds of interesting properties of f and still preserve the results?
Now that I know of, because I didn't state the pigeonhole principle exactly, but you can demand that it is a bijective function, that it is a one-to-one and onto, and on top of that, I don't know. Do you have anything in mind that you be interested?
Yeah, I'm not. Yeah, okay. I didn't quite prepare this. Of course, you have all this kind of thing of embedding.
But in a sense, one cannot expect that you can add too much, because this this function is kind of random, that you would add some random object, or at least has to be randomly looking, otherwise you won't be able to do it.
Right.
As soon as it is structured, then you probably cannot prove it. But there are other principles like which are known to be independent of this, that you may have a partition into two element sets of an OR set and things like that.
Okay, I don't have a good example, but if I think of one, I'll email you about it. And I also had the yeah. So if as I do now and then you work constructively, then the hierarchies that you get, at least if they have to cover all formulas, cannot be given in pre-next form, and so and of course, if you look at Peano Arithmetic, it's understandable that all we have so much power, and so the quantifiers are so powerful compared to the propositional connectives that they win, and so indeed you can formulate all, reduce all formulas to the pre-next form. So, but you would but constructively, of course, even in hiding arithmetic, you cannot do that, right? So the constructively implication is also extremely powerful, and it's just the collaboration between implication and the quantifiers that makes things tick. But so now you're making the quantifiers weaker by looking at strongly bounded, etc. But still, it seems that the quantifiers are still classically so much stronger that the hierarchies that you look at are pre-next.
Yes.
So, yeah.
Yes, from some point on. So you need you need to start with sufficiently strong fragment, but I'm sure that from S1 to you already should do it. Should be able to have just the prefix of bounded quantifiers followed by a sharply bounded.
But so below that it will break down. So you need more complicated.
There is some problem, but I don't know exactly how strong theory you need. But you need something. Not sure as that it is S12, but it also depends what language you use. So if you add something more to the language, like what Emil Ježábek did with T02, he added one more function symbol and make this theory more natural. And this may also help. But I'm sorry, I don't remember this. But definitely, from some point on, you can do it this way.
Okay, thank you. Okay, more questions.
Yes, I do have a question. So, with regard to this model theoretic lower bound for proof complexity, so so basically this proof of course on the surface look very non-constructive. So basically, you prove indeed you prove that the at some point, this it becomes hard to prove pigeonhole principle, but from the proof, it's really not clear when. So maybe it happens in, I don't know, say for the depth 3 Pragi, it happens in, I don't know, something like Graham number, whatever, so something extremely late point. So could you extract more constructive information from this proof to give some?
Yes. Definitely, people did it. Alex Wilkie wrote. I don't know whether it was published, but there was a manuscript. Actually, I think it was handwritten. Even I don't know. It was circulated where he extracted the combinatorics from the proof. So it's not hopelessly non-constructive. It's if you work through it, then it is fairly constructive.
Right, yeah, thank you.
Still more questions.
Can I ask one more question?
Yes.
Do you know any results of complexity over real numbers, complexity theory over real numbers or complex numbers? I mean, all the complexity theory seem to be done over natural numbers. Are there any study of generalized complexity over real numbers?
Yes, there is. Let me check if I have a book about it.
Okay. The BSS, okay. Yes.
So you may have heard about it.
Yes, I heard of it.
So they have, it's a very interesting theory. It's they have versions of P versus NP for real numbers, in fact, for any field. And people are still working on it. That's a possible approach. It's possible to the advantage of these algebraic things is that there is more theory around. So it's seems like more likely that people would solve these problems and then learn something and eventually solve P versus NP, the discrete version. But these continuous version seems to be more amenable.
Okay, thank you.
I'm sorry, I forgot to connect my computer to the battery is just not want to. It's very low. Let me connect the computer to. Okay.
Okay, well, we still have
Just about to.
room. Sorry. We still have room for one question, so is there more?
Okay.
If Yong, you still have a question?
Yeah, if no one, yes, my flavor asked the last one. Yeah, as far as I know, what's the weakest system to prove the Gödel's second incomplete theorem?
What is the weakest system in which one can prove the Godel theorem?
The weakest just means that some fragment of P, just for example, in the hierarchy of I sigma and this kind of style. Yeah.
Yes, you can prove the Gödel theorem. I mean the unprovability of consistency, or what, or incompleteness, or
Yeah,
I think Yong said the second incompleteness.
Yeah. Just as far as we know, what is the weakest system we can prove the Gödel's second incompleteness theorem? I mean that the weakness system T, such that we can prove that T cannot prove the consistency of T. Yeah, this is what I mean.
Okay. Yes, so this is actually a question I was interested a long time ago, and it turns out that in a very weak systems, just you don't need to even have to induction. You just need to take these basic axioms for addition and multiplication, which is called Robinson's arithmetic. Then, in a sense, this theory is, even this theory doesn't prove its consistency. But then, of course, there is the question how to formalize it so that it makes sense, because this theory is proving very little. But definitely, in these weak systems, you can prove it. But unfortunately, unlike for the fragments of Peano arithmetic, you cannot use it to separate the fragments. So the fragments I sigma n and I sigma n plus 1 are separated by the consistency statement. But what happens in these weak fragments is that you cannot prove, even in a fairly strong fragment, you cannot prove the consistency of a fairly weak fragment. So you cannot use the consistency statements to separate these theories.
Okay, so do you mean the weakest one is Robinson's arithmetic Q, right?
Yes.
Oh, okay, thank you. Okay.
So this is maybe in my book with better high, the other book.
Oh, in your book. Okay.
Yes.
Okay.
Okay, maybe. So there's still a very urgent, quick question. We still have a little bit of time, but if not, then we can thank Pavel for his talk.
Okay.
Thank you for listening. Thank you for inviting me, and I was glad that I could present something. Thank you. Bye-bye.
Very much.
Bye.